Okay, so this module is going to introduce you regular expressions and how regular expressions can be turned into non-deterministic automata. Okay, so right. So regular expressions are a shorthand, an ASCII-based shorthand, you can say, for non-deterministic automata. And regular expressions are nothing but syntactic terms that express a set of regular strings, regular language fragments. So epsilon is a regular expression which denotes the empty string, actually the language containing the empty string, which is the unit language. Then if you have a symbol A, just like that, in a certain alphabet, it is going to be the language containing just that symbol. And concatenation of regular expressions build up longer regular expressions. So without further ado, let us run this notebook and see what we can experience. So when we run this notebook, what we can do is not only exercise the regular expression constructs, but also see the non-deterministic automata being drawn. Then I will introduce to you how regular expressions are converted to NFA through a context-free parser. That is an interesting insight that lends a certain insight to you. So for instance, here is a set of notes I made, and this could be rendered in mathematical notation if you process it as a markdown language. In any case, come here and exercise the first cell. So regular expression to NFA gives a certain regular expression in a string and then draws it. So let us start from the beginning, RE2NFA. That actually takes a regular expression. So the first regular expression we are going to exercise is the epsilon one. So it actually gives you an NFA. You can actually see how it gives you an NFA in terms of the structure. And then all that we did was to parse and print it as an NFA. So now if you take a string A, which is a regular expression for a single symbol, that'll be converted to an NFA, which looks like that. It is a non-deterministic automaton, which starts from a certain start state and engages in only one move. Now, you can do concatenations of regular expressions that are also regular expressions. And the construction, the standard construction suggests that you build an NFA for each of the symbols and then run from the end of one of the NFA to the other, turning the first final state after A into a non-final state because we had to accept a B also thereafter. So you could actually now start running cell by cell and see if you have AB and then followed by C or D. What happens is something that is interesting that can be understood by first running AB, A plus B itself. So A plus B itself is a disjunction of two symbols, either it could be A or a B. And remember that our NFA need not start with a single initial state. That comes in handy. So when you run AB followed by C or D, we simply build the AB NFA and C or D NFA. So if you want to, you can convert this into C or D, and that will be like so. And the C or D NFA comes later. And so from the final state attained by finishing at B, after B, you can connect to the initial states. So this way we are modularly compiling REs to NFA. And now when you come to A star, we don't know what the A star form is, so let us exercise that. So dot object NFA of the A star would be a star NFA, which doesn't work because RE2 NFA has to be done. Then only it actually produces a NFA that can be drawn. So now A itself is generated, and the star construction takes and adds a new start state, which is also final state. This way, you're ensuring that epsilon is in the language. And then you transition to every initial state. And from every final state, you loop back. So let us try whether that is happening. Let us try to see what the star of C or D would be. So instead of A star, we'll try to do C or D star. So we know what C or D is. It's the disconnected C or D machines. So now you transition from the single initial and final to every start state. And then from every final, you loop back. You can see how this block C or D is inserted in the star construction. So this is all what we care about at this point, how regular expressions are turned into NFA. And then, of course, the rest of the pipeline takes over. You could convert everything back to a single DFA. So if you have AD star, it'll be an A followed B, and then the star construction is engaged in. And let us see whether we have NFA to DFA is defined. So we could, at any point, call NFA to DFA. So for instance, if this looks interesting, A or B followed by C, even though I put a blank here, the precedence rules associativity, in this case, the precedence is the concatenation is like multiplication, so it binds tighter. So B or C is parsed, and then the whole thing is quantity fused. So if we were to do a dot object, DFA, A or BC, you see that you are building an NFA for A or BC and then converting it to a DFA. And if we see it with black holes, it actually shows that after the A or BC, and then you can put fuse edges. You can see that after the A or BC, we are going to the black hole. So C itself is not defined from the start state. After a BC, again, you go to the black hole. So this actually shows the full power of the tooling. You could actually understand the piecemeal construction of machines. And at any point after RE2NFA, you can see the full effect of NFA to DFA also. So how is the parsing of context-free parsing of REs done? So we use a parser generator called Py, which is Python Lex and Yak, written by Dr. David Beasley. It's a very interesting piece of software. You can use it to build experimental simple compilers, as Dr. Beasley has taught in his class at University of Chicago, taught long ago. He's now a Python developer, tutor, promoter. So if you continue on, what you see here is the context-free rules that define regular expressions are introduced here. So the tokens that you need, this is a concept that I'm jumping ahead a little bit and introducing. But suppose you were to define a parser that parses regular expressions, then you need to recognize an epsilon or a string, which is a single symbol, or a left or right parenthesis, the plus and the star. So if you run this one, it gives you the parsing rules. So for instance, a regular expression is a regular expression or a concatenation or expression of two regular expressions. Regular expressions are simply concatenation expressions. Concatenation expressions are concatenation expressions followed by ordinary expressions. These are the grammatical rules that we'll be studying later. And concatenation expressions are ordinary expressions. Ordinary expressions are ordinary expressions followed by a star or a left parenthesis expression, right parenthesis. So in each of these, we are building an NFA as a compiled piece of code, you can say. And there are other basic cases in the grammar scheme that are defined here. And these are the helpers. So there is a make star NFA that takes an NFA and makes a star out of that, puts a star loop. So it actually opens up a new dictionary for the delta that will be used. And then it is adding all the original NFA states and a newly introduced state, which is also a final state. And then the alphabet is kept the same. And then the delta is changed to introduce the loop back for the delta, the loops that you introduce during a star. So now we can actually see how these are parsed and which NFAs are run. So we can run certain cells here. And these are, again, introduced to not only show the parse tree, but also the NFA. So the parse tree and the NFA resulting from epsilon are shown as N and a T. This is a package that will be illustrated again. But suppose I now do something like this. Into T2 is a draw parse tree. I'm parsing these two. So what is the N1 parse tree, N1 NFA? So this is the N1 NFA resulting from this regular expression. And what is the parse tree for that? So this is the parse tree for that regular expression. So what I ended up showing you here is, it is showing you that there's an A star and a P star and a C followed by SC. And these two are disjuncted and parenthesized and starred. That is the N1 T1, A star, B star, or CC star. That is resulting in this NFA and this parse tree. So you do not need to study this further at this juncture because we haven't introduced context-free parsing, but it is clear that the Jove material allows you to be teaching not only what regular expressions are and how they convert to NFA, but you can also introduce simple parsers, lexers, and parsers in this case. And the lexing is done to understand the tokens. And that is simply accomplished by picking up the lexemes or symbols that represent tokens. And these are the tokens. And then the tokens are consumed by the parser generator. So I hope this was an engaging experience to not only understand regular expressions in NFA, but also how the mechanistic details are implemented. And we'll be talking about how the ply parser can be built when we come to the context-free modules. So until then, goodbye.